Okay, so we are going to start the course on power electronics. So, I am sure all of you know what is electronics. Electronics is basically going to have semiconductor devices which control electronic circuits. Whereas, if you look at power electronics, you should know the applications basically. The applications are right from mobile phone chargers, which is of only about a few watts rating, to if you look at industrial drives, which may be of megawatt rating. So, the entire range generally is covered by power electronic circuits. So, if we talk about industrial drives, they are of megawatt rating, whereas when we talk about normal electronic circuits, they are only of a few watts rating. But we are looking at power electronics, which is consisting of both power, which is high power circuit, as well as electronics, which is low power circuit. So, power electronics essentially deals with power semiconductor device circuit. That is the circuits that are made up of power semiconductor devices. Some of the power semiconductor devices are like power diodes, SCRs. We will be talking about each of these devices later. Then you can say power BJTs, power MOSFETs. So, all these devices, when you talk in electronics, you will be talking about just BJTs or just MOSFETs, and you will be talking about diodes, whereas here we are adding a prefix power. So, power diodes, power BJTs, power MOSFETs and IGBTs. So, all these things are going to be ultimately connected in different circuit form to make either rectifier, which is AC to DC converter, or inverter, which is DC to AC circuit, and so on. So, we will be dealing with power semiconductor devices which are connected into different circuit format, and they will be used for different applications, be it mobile phone charger, be it a big rectifier, or be it an inverter for industrial drives. That is what we are going to talk about in this particular course. Okay? So, in electronics, normally we handle 15 volts or 5 volts, nothing more than that. So, let me say what is power electronics versus electronics. So, electronics, you are going to handle only 5 volts, 15 volts, I would say plus or minus 5 volts, plus or minus 15 volts, 3.3 volts and so on and so forth. And as far as currents are concerned, they may be microampere, milliampere, at the most a few amperes, not even 10 ampere, it will be generally less than that. Most of the time you will handle very, very small power levels which will go of the order of a few watts or a few milliwatts, nothing more than that. Whereas in power electronics, normally the same electronic circuits may be made bigger to handle higher current, cross-sectional area should increase. To handle higher voltage, the length should increase. So, if I increase the length, it will be a high voltage device. If I increase the cross-sectional area, it will become a high current device. So, if I can handle higher currents and higher voltages, in that case, I would call that as a power electronic device. And when I put several devices or one or two devices in a circuit, I call that as a power electronic circuit. And it can handle generally controlling an electrical machine or controlling maybe a transmission system, maybe controlling the power that is delivered through the UPS, uninterruptible power supply, or switch remote power supply within your computer. All those things, whatever circuits we see in these things are all power electronic circuits because they handle a little larger power. What I mean by a little larger power is power electronic circuits can handle right from a few watts to tens of or hundreds of megawatts. So it can handle a wide range of power normally. You are going to have right from a few watts to hundreds of megawatts that can be handled by all these power electronic circuits. Typical applications. Why should we study about it? Unless there is some importance, we should not be studying about it. So your mobile charger, that's typically a power electronic circuit. If you look at the mobile charger, it is connected to a 230 volts AC mains. If you look at it carefully, it will say 90 volts or 80 volts until 270 to 280 volts. So it is known as the universal adapter. So it will be able to charge your mobile phone whether it is in the US where it is 110 volts, right? Or whether it is in Europe or India which is 230 to 40 volts. So it would be able to adapt itself to any kind of AC supply voltage as long as it is within 50-60 hertz range. India has 50 hertz and Europe has 50 hertz, USA has 60 hertz. So you will have different frequency ranges, but from that 230 volts or 110 volts AC voltage, first of all there will be a rectification that will be taking place. Rectifier is a power electronic circuit there. So it will rectify to DC. After rectifying to DC, it has to step it down to a smaller voltage, whatever be the mobile battery's voltage. Maybe it is 1.5, maybe it is 3 volts, whatever it is, it will correspondingly step it down. No transformer, of course, because DC voltage, transformer cannot work on DC, obviously. So there will be a step down converter which is also a power electronic circuit. So if I try to look at the mobile charger, I am going to have something like this. I will have first of all 230 volts 50 hertz or 110 volts 60 hertz AC. This is now connected to a rectifier. The rectifier is going to convert this into corresponding DC voltage. If it is uncontrolled rectifier with the help of diodes, just diodes, then I am going to have very clearly 2 Vm by pi. All of you know that expression, I suppose, maybe in ELL 100. Initially, we had looked at some amount of rectifier circuits. So we are going to get 2 Vm by pi approximately. So whatever is the voltage that we get, it may be 0.9 times Vrms, roughly. Okay. Now this has to be stepped down to the voltage that is corresponding to the battery voltage of the mobile. So from here I may have to have a DC to DC converter, which is again a power electronic circuit. So I would say this is a PE circuit. This is also a PE circuit, power electronic circuit. Now the output of this will go to the battery. And it has to be regulated. In case from 230 suddenly the voltage comes down to 180 volts in the grid. Still I should be able to give the same value of voltage to the battery. So there should be some amount of adjustment. So very clearly there are several functions that are associated with a power electronic circuit. One is regulation. So I have to regulate the voltage. Definitely voltage regulation has to be done. Irrespective of variation in the input voltage, irrespective of variation in the load, because battery may be fully charged, in which case the voltage will be close to whatever is the rated voltage. If it may be very, very low charge level, then in that case the voltage is going to be somewhat lower. See, if you talk about a 5 volts battery, for example, it can go until 5.5 or 5.75 volts when it is fully charged, slightly higher than rated voltage. When it is completely discharged, it can be as low as 4 volts or 4.2 volts. So you can have that much of variation. So despite those variations, the current that is going into the battery to charge it, that has to be regulated. The voltage has to be regulated. So it's not only voltage regulation, even charge or current regulation. Both have to take place. Second thing we may require is, we will have some kind of isolation required between the input and output side. Isolation is, you don't have to have a common ground. Like a transformer, think about a transformer. In a transformer, if I am going to have this as the primary and this as the secondary, this may be connected to the ground. This may not be connected to the ground, or it may be grounded separately. You will not connect the two together. Never. Right? So the isolation takes place whenever I use a transformer, two-winding transformer, not auto transformer. Right? Auto transformer is a single winding transformer. You connect primary and secondary together. So whenever I use a transformer, I am going to have isolation between the primary and secondary. Similarly, isolation will be possible when I use a power electronic circuit. Probably I will insert a transformer somewhere. Probably I will insert something else. I'll have to check what other stuff I have to insert. So these are two primary functions of a power electronic circuit, generally regulation and isolation. Apart from that, I would also convert probably AC to DC or DC to AC, or I may convert AC to AC with variable frequency. That is, I give a 50 Hertz supply, I might like to have a 100 Hertz AC output. So AC to AC conversion is also possible, and of course the last one which I have left out, which is DC to DC. All four types of conversions would be possible. So I might like to convert the frequency, magnitude, or both. So DC, I can say it is zero frequency, right? So I can convert the frequency or magnitude or both. Either any of them is possible with the help of a power electronic circuit. So one example I gave you was the mobile charger, right? Another example, when we talked about induction motor, for example, you guys had done a variable frequency induction motor drive experiment in the laboratory. What was sitting inside that box was actually a rectifier which was initially converting the 50 Hertz AC into DC. Subsequently, there was an inverter which will convert that DC into any variable frequency AC. So that is a typical example of creating an adjustable speed drive. If I want an adjustable speed drive, I would be able to use an AC to DC converter and then a DC to AC inverter. That will essentially enable me to get a variable speed drive or adjustable speed drive. So this is another example, right? So if I look at power electronic system in general, what consists of a power electronic system? In a power electronic system, I am first of all going to have a source. That source could be DC, it could be AC, whatever it is. So 50 Hertz, 60 Hertz, or just a battery which is a DC source. From here, I am going to have a power converter circuit, which is actually the heart of my power electronic system. So it is going to convert maybe AC to DC, DC to AC, whatever it does. It is going to have some functionality. Now this power converter system will give an output. The output will be in the form of a particular voltage and particular current, right? So I will have some voltage and some current. So let me say them, call them as instantaneous values, small v and small I. If it is three phase, of course I will have VA, VB, VC, IA, IB, IC, obviously. So I'm going to have voltages and currents. Now I will have a load here. The load could be an induction motor. The load could be a battery of the mobile. It could be like a keyboard, musical keyboard, which has, in olden days we used to call it as an eliminator. So it is essentially a charger, basically. It is allowing you to convert AC into DC, right? So this is the load. Now the load might require only 5 volts. It may require 400 volts and 50 hertz if it is an induction motor, line to line voltage. It might require maybe 25 hertz and 200 volts if I want to run it at lower speed. So I need to know the requirement of the load. So what I will have here will be a sensor or a transducer. So what I will do is to sense from here the voltages and currents. Maybe if it is a battery, it is good enough for me to sense only the voltage and current. If it is an induction motor, I need to sense voltage, current, as well as maybe torque and speed. So depending upon the kind of load, I may have more than electrical quantities being sensed. So I would rather call it as a sensor or transducer, because transducer converts mechanical signal into electrical signal, thermal signal into electrical signal, and so on and so forth. Invariably, I would like to convert that into electrical signal because I am by and large handling electrical circuits. So everything converted into electrical signal will give me a lot of advantage in terms of processing them. So I would first of all like to sense the mechanical quantities or electrical quantities or thermal quantities and so on. For example, an air conditioning system, right? How does the compressor go off? Because it senses the temperature. Maybe you have set it at 25 degrees and the room has already reached 25 degrees. So the compressor will go off. So for that, you have to first of all convert the temperature into an equivalent electrical quantity in all probability, so that the control system realizes, yes, I have already reached the temperature, so I can turn off the compressor, right? So you will have basically a sensor or a transducer. Now what comes out here is actually the sensed quantity in the form of an electrical signal. Okay? Now, I may have a controller here or a control circuit. I may call this as a control circuit. So, in the control circuit, one will be a reference value. I may require 25 degrees centigrade. I might require 5 volts. I may require 400 volts and 50 hertz. So, the reference value will be given as one of the input, and the sensed value will be given as the other input. Now the control circuit is actually the intelligence or the brain of this entire power electronic system. That is going to now make a decision based on what kind of inputs it is getting. It is going to make a decision whether I have to reduce the current, reduce the voltage, increase the frequency, all those things it will decide. So once it decides, it is going to give this to the power converter in all probability through an isolation circuit. Because I would not like to mix the ground of electronics or the control portion with that of the power portion. Because power portion will have a thick conductor going to the ground. So the currents that are flowing are of the order of hundreds of amperes. Whereas electronic portion will have only milliamperes or 1 or 2 amperes. So if something goes wrong in the power portion, I don't want that current to circulate through the electronics portion. If it circulates, it will end up burning the entire electronics portion. So the grounds invariably have to be isolated. So the isolation circuit essentially functions as a protection against burning the electronic portion of the circuit. If there is a problem in the power portion, that will not affect the electronic portion. And apart from that, I might require an amplification also. The isolation is meant for, decoupling the grounds of the electronic portion from that of the power portion. Whereas amplification is required because the power electronic circuits are big. They will not work on milliampere. Even the base drive that you require for a transistor, power transistor. For every power device, I will add a power. Instead of saying transistor, I will say power transistor. Okay? So, if it is a diode, I will say power diode. Because power diode means it indicates it's going to handle a larger power. So, if it is a transistor, if the base requires, let us say 1 ampere, the amplification factor probably is about, 10 ampere or 15 ampere maybe is going to flow through the power circuit, but the base will be some fraction of that. Collector current will be much higher, base current will be much smaller. So maybe the base current is 1 ampere. In all probability, my electronic circuit, which is actually this control circuit, that may not be able to give even that 1 ampere. So I will need an amplification circuit. So in all probability, I will need isolation and amplification. Both have to sit in between the control circuit and the power electronic circuit. So this is the overall structure of a power electronic system. So we will have a source. It will go to a power converter circuit, which is going to convert the voltage magnitude and frequency as per the requirement of the load. The load will function once it gets the supply. So the load is going to give some output. So the voltage, current and the output, everything will be sensed. After sensing everything, we compare it with the reference values that we want to achieve normally, and then accordingly we take a corrective action until the error becomes 0. This is the error, right? When I compare these two, so if I say that this is V, star, generally we call the reference values as star. I star, V star, omega star. Omega is speed. Torque star, whatever. So star is generally indicated for reference values. Okay? And the actual values generally I specify as ACT will be the subscript. I will generally say V actual, I actual, omega actual, TE actual, and so on, electromagnetic torque actual. So these two are compared, which actually comes out in the form of an error. Right? That error is processed by the control circuit. And that's what actually adjusts the voltage or current or whatever output of the power electronic circuit such that the error becomes 0. This is the overall configuration of the power electronic circuit. We are going to mainly concentrate on this portion. But as a power electronic engineer, I need to know some amount of sensor and transducer working. If I don't know, I can't deal with power electronic circuit. I have to know how to isolate and how to amplify. If I don't know, I cannot again design a power electronic circuit. So I need to know some amount of analog electronics. Maybe not as much as Shourie knows, but I have to know some amount of analog electronics, some amount of digital electronics, some amount of sensors, some amount of transducers, large amount of characteristics of the load. So if I am talking about a battery, I should know at least something about the battery. If I have to control a machine, I better know what the machine can do for me. Right? So I should know the dynamics of the loads. I should know the dynamics of all the electronic circuits, sensors, transducers, amplification circuits, isolation circuits, and so on and so forth, apart from knowing the actual power circuit. right? Unless I know, I cannot control the power circuit. I don't know the power circuit, how will I control it? So I better know all these things. And most of the times, we model and simulate these circuits before we really put it on the hardware. So modeling and simulation is another aspect we need to know. How to model a power electronic circuit. How to make a control system configuration for a power electronic circuit. So power electronics basically becomes interdisciplinary because of all these areas involved. So I told you that analog and digital electronics. And these days we use a lot of computers and microprocessors and digital signal processors. So we need to know definitely at least something about the assembly language and, other internal machine language of the processors, at least to some extent. So we should know some amount of computer technology, right? We definitely need to know to some extent physics of the devices. We may not know again as much as whoever taught you physical electronics, but definitely we need to know how much of heat is going to be generated within the circuit. If I don't know, then I will not be able to make sure that it doesn't conk out. If excessive amount of heat is generated, then it will get overheated and it will conk out. And for dissipating the heat, we use something called a heat sink. This is the heat sink. You can see, it looks like an insect. So many legs, right? This is known as heat sink. Normally what we do is, you can see that there is a hole, right? I'll circulate this, not a problem. Generally to that hole, we'll put the device and bolt it together. This is a device, small device, okay? It may be a transistor or thyristor. I didn't check exactly what the device was. Maybe an IGBT, spoiled IGBT. So from the lab, I just picked up, okay? So this is a device. The device, as it is, if I connect it to the circuit, it will generate a lot of heat and it will conk out eventually. So to dissipate the heat, if I put a black body attached to it, its body, then the heat is going to be transferred to the black body will radiate it. To increase the surface area, these legs are there. It is essentially increasing the surface area, right? So typically, for knowing how much heat will be dissipated, I should know at least the physics of the device. Pass it on. I'm just telling you that these two have to be put together so that it is bolted together. There is a hole here, there is a hole here. They will be put together and bolted, right? So I should know device physics to a large extent. I should know modeling and simulation. And I should know transducers, sensors. I should know the working of control systems. Of course, machines and drives goes without saying, right? Because I'm controlling most of the times those things. I better know it, right? So power electronics happens to be interdisciplinary in nature because of these things, right? Now, apart from this, as we know, when I use a rectifier, it is converting AC to DC, right? So if I am having an AC supply here and I put a simple diode here and here is my load, this is a half-wave rectifier, simple half-wave rectifier. Only in the positive half cycle the current will flow. Negative half cycle current will not flow. So if I look at the current at this point, it will have only half of the sinusoid. The other half will be missing. What we want from the power system normally is the currents and voltages should be as much as possible sinusoidal so that it doesn't create a headache. I don't want harmonics. I don't want DC. Because the machines are generally generating sinusoidal currents. They would like to supply sinusoidal voltage and sinusoidal current. If I am asking them to deviate from that, they can misbehave. So, the power electronic circuits create automatically some amount of misbehavior. Whether we want it or not, When I convert AC to DC with the help of a half-wave rectifier, I am automatically creating an aberration in the waveform. The waveform is not anymore sinusoidal. It is non-sinusoidal. So, there is something called power quality we talk about. Power quality essentially deals with whether the voltage is sinusoidal, whether the current is sinusoidal, whether it is only 50 Hertz, not deviating from 50 Hertz, whether the power factor is unity. All these things are generally specified as the power quality indices. There are several power quality indices. One is voltage, the second one is current, whether they are sinusoidal in nature, whether they are at unity power factor, whether they are at 50 Hertz. All these things are examined and said that if all of them are adhering to the normal standards, we say power quality is very good. If they are not adhering to the standard, then we say it's not good. For example, our power system is supposed to be a very weak power system because most of the times our demand is higher than the supply. The demand is always larger than the supply, because of which voltage sags. Voltage will not be at 230 volts or 240 volts. It may come down to 180 volts. So the equipment which is expecting 230 volts, if it gets 180 volts, it's not a good thing for the equipment. So our power quality normally is not good most of the times. And added to that, we put so many power converters. So obviously power quality becomes worse. So we guys are the culprits. We power electronic engineers are the culprits who make the power quality much worse. But power converters definitely help us in controlling the voltage, controlling the speed, controlling the torque, controlling any process. So obviously we employ a large number of power converters these days. But we also essentially make the power quality bad. So power electronics again comes to rescue to improve the power quality. So on one side we create the problem, on the other side we strive to solve the problem. So power electronics is the root cause of the problem, but some of the power electronic circuits we again employ to improve the power quality. So we call them as power conditioning or power quality conditioning. For example, SMPS and UPS. What is UPS? Uninterruptible power supply will make sure that 230 volts, 50 Hertz is given to my computer, no matter what. SMPS makes sure that plus or minus 5 volts, plus or minus 15 volts, 3.3 volts, all of them are given to the computer circuits, whichever require whatever voltage. So, I am creating a problem with other power electronic converters, but SMPS and UPS take care of these problems. They essentially insulate the actual computers from these problems. They supply the actual value of voltage and frequency that is needed by the computer. Right? So, power conditioning is generally done by UPS, SMPS and such circuits. Those are also power electronic circuits. Right? So, if you look at the application of power electronics, it is plenty. But before that, let us try to see what all different types of power converters are there. As I told you, in power converters, I can have AC to DC, which I may call as rectifier. Right? When I convert AC to DC, normally we will call that as a rectifier circuit. Right? I may have DC to DC, which normally are known as DC to DC converters in most of the cases, but some people call it as choppers. They chop the voltage and then convert it into another value of DC. What I am trying to say is, if let us say originally the voltage is this is 20 volts, right? I want only 10 volts. on an average basis. I cannot make 20 to 10, obviously. If I have to do that, I have to use two resistors, say 10 ohms each, drop off half the voltage in 10 ohm, the other 10 ohm will have 10 volts. I don't want to do that because it is lossy. So rather than using a potential divider, if I try to do it this way, maybe I have 20 volts coming for T by 2. Again 0 volts coming for T by 2. Again 20 volts coming for T by 2. 0 volts coming for another T by 2. What will be the average value? 10 volts. Right? Looks kind of strange. Right? Because how will the motor know you are giving only for half the time? It will start rotating. That's what you might think. But this I will do at kilohertz or higher frequency. Hundreds of kilohertz. Whereas motor has a huge time constant. Right? Mechanical time constants are generally very large. It's going to take a while for the motor to realize that, okay, I have to pick up speed quickly because they have given me 20 volts. Right? And they have not given me any voltage, let me just come down to 0 speed. It's not going to happen because the inertia is going to take a while before really the motor responds to the variation in the voltage. Because of which the average value seems to be 10 volts. So this is what is DC to DC conversion, for example. We chop the voltage for 50% of the time. We apply the voltage for 50% of the time. So we call this sometimes as chopper. Right? This is DC to DC conversion. We will have AC to AC converters as well. So I can do the same chopping in AC. Imagine maybe I have a switch. Okay. So if this is my original AC voltage, I keep the switch on for only some duration, and again I keep the other switch probably in the opposite direction on only for some duration. What will happen? RMS value will decrease. If I have it on for longer, I'm going to have a higher RMS value. If I have it on until here, for example, right? So which means this entire thing will become my voltage. Right? So I can vary the magnitude by controlling an on-off switch. I can simply have an on-off switch in positive direction as well as negative direction. So imagine I have one diode like this, another diode like this. But if it is diode, I can't control, so I have to have another gate terminal. The gate will open the conduction or close the conduction. So generally we call this terminal as gate, this terminal as anode, this terminal as cathode. 3 terminals. Right? So the gate will allow a device to be turned on or turned off. So I will be able to delay the conduction. It can start at 0 or it can start at 90 degrees or it can start at 130 degrees. Depending upon when I give the gate signal. So the RMS value can be definitely adjusted. So this is a typical AC to AC converter circuit. Okay? But please note, the frequency is not changing. If it is 50 hertz, it will be still 50 hertz at the output. It will not be anything different. So transformer is like AC to AC converter. The frequency does not change, but I can reduce the voltage. Right? Transformer is like an AC to AC converter. Only thing is, transformer is very bulky. It's really, really bulky because you have iron core and windings and so on and so forth. Whereas power semiconductor devices generally are very small. They are really miniature. What I have circulated, you can see that is about 10 ampere and 400 volts device. Not chota sa. It's a real small miniaturized configuration. The heat sink occupies more space than the device itself normally. right? So miniaturization, if it is required, power semiconductor devices are the solution, really. Okay? So AC to AC converter is sometimes known as AC chopper. There is one more type of AC to AC converter which we will be dealing with, which right now I am not going to explain, which is known as cycloconverter. We will be dealing with both these circuits. Okay? Last but not the least, DC to AC. DC to AC is generally known as the inverter. So the inverters are used in plenty of applications. For example, I told you induction motor speed control. You will need an inverter. At home, many of you guys will be having an inverter, especially the power outages very frequent in some places, they will require an inverter, right? So inverters really find application. UPS has an inverter. SMPS might have an inverter inside. So there are n number of applications where inverters are used. So what we will do during this course is, each of these circuits we will be looking at with different configurations. For example, if I am looking at AC to DC, it can be single phase AC, three phase AC. Half wave rectification, full wave rectification, right? So there are different configurations we will be dealing with. We will be looking at different cases like resistance load, RL load, RLE load. E is a battery, or if it is a DC motor drive, back EMF, right? So we will have to look at all those things. So I am just telling you, for example, for the rectifier, single phase AC, three phase AC, half wave, full wave, R load, RL load, RLE load, RC load, and so on. So many things we'll have to look at, right? So we'll be looking at each of these circuit configurations with variety of inputs and different kinds of outputs we want. For example, DC to AC, I may require single phase AC, three phase AC, right? So we'll be looking at all those circuit configurations and how to control them, right? And finally, what are their applications? And how to implement the hardware. At least I'll give a small inkling. I'll have to at least give you a little bit of idea as to how to implement the hardware as well, right? So this course is about all these converters, their control configuration, and their implementation aspects, and finally application. This is what it is. Okay? So we will start this course with the devices first, because you guys have not really studied devices except the physics of the device as such. We will be talking about three different kinds of devices. One is completely uncontrolled. Uncontrolled devices, diode. For example, if I forward bias, it will conduct no matter what. If I reverse bias, it will stop conducting. I don't have any control. It just will conduct no matter what if you forward bias it. So, uncontrolled device, typical example is diode. We will call it as power diode because it is going to handle a larger power. That's all. Otherwise, it behaves exactly like the normal diode. Normal silicon diode, if you say 0.7 volts is the voltage drop, if it is a diode of 6 kilovolt rating, for example, it will have a larger voltage drop because it will be longer. So it is like a little larger resistance, as simple as that. Otherwise, the behavior is essentially the same. There is hardly any difference between an electronic diode and a power diode. There are devices which can be controlled during turn on, which cannot be controlled during turn off. Once you turn it on, it's as good as opening a tap. That's it, you can't close it. It will keep on conducting. So those devices are known as semi-controlled, or it is only on controlled, off not controlled. You cannot control the turn off. Typical device which we will be looking at will be SCR, or silicon controlled rectifier, which is also generally commonly known as thyristor. And what I showed here, this is a thyristor. This is a thyristor. It will have 3 terminals, an anode, a cathode, and a gate. In the gate, if you give a signal, it will start conducting. You can't turn it off unless it is reverse biased. When it is reverse biased and the current goes to 0, it will automatically go off. And the other device, again, when you give a signal, it will start conducting when the negative half cycle comes. Because negative half cycle, this will be negative and this will be positive. So it is forward bias, so it will start conducting. Right? So that also has to go off only when it is automatically reverse biased. So these devices are good in some applications, not in all applications, definitely. These are semi-controlled devices. So in these cases, on is controllable, off uncontrolled. Okay? The third type of devices is fully controlled. It can be controlled during turn on as well as turn off. For example, a transistor. You give a base drive, it will conduct. You don't give a base drive, it will not conduct. Right? So it can be turned on and turned off as per your requirement. So both on and off are controlled. Right? Both will be controlled normally. And those devices are the most useful generally, because you can control everything about them. But unfortunately, the ratings of these devices are still limited. A lot of research is going on in devices because of this reason. The research is only concentrating on mainly 4 factors. One factor is to increase the rating, power rating. Voltage rating should be increased, current rating should be increased. Ideally, we would like to have infinite rating. You apply any amount of voltage, any amount of current. But we are not yet there, clearly. So the first and foremost is to increase the voltage as well as current rating or overall power rating. The second is to make sure that the drop across the devices are minimal. How much ever we may say these devices are close to ideal, there is hardly any resistance. When diode conducts, it's only 0.7 volts. But every 0.7 volts matter. Right? So we would like to, as much as possible, reduce that forward voltage drop if it is possible. And the forward voltage drop multiplied by the current carried by the device. That is the power loss across the device. That is what is heating the element, that particular device. And that is what is the reason for the device conking out, ultimately. So you have to put big heat sinks and so on. So if I can reduce the power loss across the device, nothing like it. So the second effort is generally towards on-state losses or on-state resistance reduction. And the third effort generally in many of these devices is towards high frequency of operation. So if I look at I can't say which is the highest priority and which is the lowest priority. So research essentially concentrates on power rating, increase, loss, rather on-state loss, reduction. The third one is frequency of operation. How much ever we may say that it turns on in microseconds, it turns on in nanoseconds, we want to bring it down to 0, literally. Until now it has not been possible. If we are able to reduce the turn on and turn off time to really minimal, we must be able to go to 10 power 12 hertz or even more. But right now we are able to go until megahertz. Not really beyond that. So, if the frequency of operation of the device is increased, that means turn on and turn off is very quick. But turn on and turn off can be quick only if the charge carriers can be emitted quickly and charge carriers can recombine quickly. Recombination essentially causes the off state of the device, and emission of the charge carriers causes on state of the device. So this requires some finite time. Maybe nanoseconds, maybe microseconds, but still. So a lot of research is going on towards this, reducing the on and off time of the device, which will enable it to operate at higher and higher frequencies. Right? So frequency of operation, whether it can be increased further. This is the other effort. And last but not the least, nobody is making devices for charity. Everybody is business. They are essentially doing business. So if you can bring down the cost of the device, nothing like it. People would go for your device if you bring down the cost. Right? Taiwanese devices are really low in terms of their cost. So if we are given, say from Fuji, Mitsubishi, and say international rectifiers, which is in America, and a Taiwanese device, many of us go for Taiwanese device if it is not a very critical application, because it's generally lower in terms of cost. Right? So the fourth one is cost and size reduction. So these are the major focus of many of the device research. And we are essentially seeing giant leaps almost every decade. When I was working with my MTech project and PhD project, I finished my PhD in 1992, we could use only thyristors, nothing else was available. Then came power transistors, then came power MOSFETs, then came IGBTs, insulated gate bipolar transistor, IGBT. Then now IGCTs have come out. Integrated gate commutated thyristor. Anyway, I'll give you different devices, what all we are going to study in the next few classes. So, apart from all these devices, what is available, although diodes are uncontrolled, they are also used extensively in many applications, although they are uncontrolled, because they are the cheapest and they are available at the highest power level. So wherever I want a very high power rectifier, generally diodes are the best choice. Then come thyristors. Okay, that is the way normally we go for. So the choice of the devices depend upon what is the frequency of operation you want, what is the kind of power level you want, right? And what is the kind of size limitations you have, and so on and so forth. All those things decide really what kind of devices you are going to choose for your particular application, right? I will not really go into the details of application now because it may not make sense now. We'll try to devote a couple of classes towards the end for applications of power electronics. I have only told you a few applications what you know about already, so that you realize power electronics is an important course. It's not, something that padna hai kya kare. Not that kind of attitude, please. Okay? So let us try to first of all look at the topics that we are going to cover and roughly how many hours that we are going to devote in each of those topics.